Well, good morning, everybody, to Monday's edition of AP Calculus BC Live. I am sitting here live in the set. If you recognize it behind me today, this is the set of the TV show The Office. I mentioned last week that I am an obsessed fan of The Office, and so I thought it would be only fitting today to use that as my background, because we're going to see several Office quotes throughout the presentation today. Once again, thank you to the talented Kate Yetman for our intro music. It's really hard, by the way, to listen to that in the beginning and not start dancing, but I realize my webcam is on, so I don't want to dance in front of everybody and mortify those of you watching, most importantly, mortify my own children. We're looking today at topic 10.13 in the curriculum, and if you're like me, that doesn't really mean much to call things by number. So 10.13 is talking about radius and intervals of convergence of power series. In case you're new here today, we did this again. In case you're new, my name is Brian Passwater. I'm a high school teacher at Speedway High School, and last week I shared with you the tattoo that I got on my arm last year, my one and only tattoo of the zeta function. My wife calls it my friend finder, because if anybody recognizes it in public and knows what it is, that's how I meet new friends. Needless to say, my friend list, my circle of friends is pretty small at this point. I also wanted to share a couple more things, because we're going to see some of these more this week. In the bottom corner, these are two of my cats, a brother and a sister. They're kind of posing with their arms out there. They're pretty camera photogenic, I think. We've got some more cats and some other animals. My wife and my children sort of buy animals and bring them home, and then I find out about them later. So I'm not really sure at this point how many animals are in my house. I know we have a third cat somewhere running around, and probably some couple other things as well. And then on the other side of the photo here are my adorable little children. They're much older now. They're in high school. But next to them is our dog, Buddy there. They're holding him, and he was just a brand new little puppy. And I wanted to show a picture of Buddy, because you're going to see him today later on in a lesson. But also on Wednesday, I'll be back. Tomorrow, Tony is going to talk about ratio test. It'll be a really, really good and powerful lesson that we're going to need for this year's exam. But on Wednesday, I'll be back, and we're going to attempt to clone my dog Buddy on Wednesday. So hold out for that on Wednesday. We're going to attempt to clone my dog live here on AP Calculus BC Live. So don't forget to be here on Wednesday at 9 a.m. Eastern time to see if we can successfully clone my dog. You heard us say this multiple times, but in each one of these videos, in the bottom in the comment section, there's a link. And if you'll click on that hyperlink, you will go to the Dropbox folder that Isaac Newton has made specially for you, and that's where you're going to be able to get the handouts and all the materials that we do during these lessons. So we would really recommend, if at all possible, to get those materials, print them off prior to the lesson. That way you can follow along, do the problems with us. And one of the things that you're going to notice if you download those materials is that we have way more problems on the handouts than we could possibly do in one of these lessons. Tony and I are ever the optimists. And so we always think we're going to have all these examples. We're going to be able to get through a whole bunch of examples at the end of each lesson. And we're like, wow, where'd the time go? There's so many more examples and problems that we wish we could have done. But we purposely write additional ones that you could do on your own practice. And then each evening, each night, we will post the keys for those in the Dropbox as well. That way you can check your work. And they're not just keys, but they're really detailed solutions that our friend Ted Gott types up. Thanks, Ted, once again, that you can follow along with your work, kind of compare your work. And if you're stumped on something, it'll really show you the algebraic way to progress and solve some of these problems. All of the problems that you see on these lessons are unique. They're new. They're questions that I've written specifically for these lessons. And so, last Friday, Tony talked us through a little bit about what this new exam this year, this unique exam, is going to look like. We already knew there were going to be some topics not on the exam. And then on Friday, the College Board released some more information about it. And so what do we know? We know it's going to be a 45-minute exam. We know there will be no multiple choice, just 2 free response questions. The first one is going to be 25 minutes long, so it's a little bit longer than we're used to for an FRQ. And the second one is going to be 15 minutes, kind of what we're typically used to in the past, but that's it, 2 FRQs to assess all the things that we've learned or should know from Calc AB and Calc BC this year. And so one of the things that Trevor Packer mentioned and College Board mentioned as they've talked about this new exam is they said on this new exam, They're writing it with the understanding that students are going to have calculators. They're writing it with the understanding that you're going to have technology with you. So it's assumed to be open book or open notes. It's assumed to be that you might be using a calculator, but they want to be able to write questions that you're not going to be able to just look up an answer in a book. They're going to be able to write questions where you can't just Google something, that you can't just ask somebody quickly or have a way to cheat or something like that. They also want to write questions where you can't just type the answers in your calculator and get the answers immediately. Well, how are they going to do that? Well, I know for one thing, the College Board is very good about writing questions and writing exams, and they're going to find ways to do that. And so all the questions that we're writing in our lessons are designed to give you ideas or examples of how that might possibly look. Now, full disclosure here, Tony and I are just regular classroom teachers, just like other teachers across the country. We have no special insight. The College Board doesn't tell us any secret information because we're doing these videos for you guys. We are equally as anxious and equally as uncertain about what this test is going to look like as everybody else. But we're trying our best to prepare our students for whatever this test might look like. And so the questions that I write that we use on here in our activities are kind of our best guess, our best ideas of how we can prepare kids for what this exam might look like. So really take time to try some of these problems, because I really think if you do these problems, it's going to help you get as fully prepared as possible for this year's exam. We've been asking you to tweet out. Tweet out if you're an AP student about what you love about your AP Calculus teacher, or if you're an AP Calc teacher watching these videos, tweet out what you love about your students. And whenever you tweet it out, make sure you include the hashtag AP Teachers Rock or AP Students Rock. Today's tweet for AP Teachers Rock: thanks, Dr. Gupta, for your dedication to our BC class. You inspire each of us every day with your engaging lessons. Can't wait to get back to school with you. Hashtag AP Teachers Rock. And then our AP Students Rock tweet of the day: my AP Calculus students are amazing people. I can agree with that. I'm so proud of how hard they work and how much they care for one another. Hashtag AP Students Rock. Thank you for sending those tweets out to us. And if you have a Twitter account, don't delay today. Hop on Twitter today at some point and tweet out what you love about your teacher. Tweet out what you love about your AP students. Don't forget to include the hashtag on there, because this is how we're searching those tweets to find some to share each day. So if you tweet out today, come back and check to see whether you made the tweet list. Upcoming lessons. Well, this is the last week of new lessons, this idea where we're teaching new content. So we're going to be talking about the radius and interval of convergence today for power series. This is not one of the asterisk topics, meaning it's not going to be directly tested, but two comments I want to make about why you should still watch this video. Don't turn it off right now. Number one, there's a lot of office quotes today. That's gonna be pretty awesome. So make sure you stay tuned for that. But it would be a real shame if you made it through Calc BC and didn't have at least some exposure to power series. They play such a really pivotal, important role in Calc 2. And it would be really hard for me to let you go through a whole year of calculus, even under these circumstances, and not at least have some exposure to power series, because even though it's not tested, they really will tie a lot of things together and bring things together that are tested. And then finally, it's important because, like I mentioned just a second ago, we're going to be bringing in all these things that we've done so far that are tested today. So we're going to be talking about a new idea, but we're going to do it in context of a testable idea. And by the end of the lesson, we're going to be tying in things and reviewing the topics that are tested on this year's exam. Tomorrow, Tony's going to kick us off with their ratio test. It's our last test of convergence as tested on this year's exam. We'll spend a couple of days with Taylor polynomials and approximations. On Wednesday, that's when we're going to try to clone my dog, Buddy. He's cute enough to be worthy of cloning. Don't tell anybody we're going to try to clone an animal right now. And then Friday, we'll end up our Unit 10 discussion with alternating series airbound. And that's the title of the topic, but we're also going to be tying in, once again, all these ideas that are tested into some good comprehensive questions review for the AP exam. And then starting next week, beyond this week, we're going to be doing some AP calculus exam prep and review. And so the great Michael Scott once said, I understand nothing. If you feel that way right now, if series is feeling a little bit overwhelming, or calculus or Calc BC is feeling a little bit overwhelming, and you've gotten to the point that you feel like you understand nothing, tune in each day this week, and then especially tune in for this review prep, because we're going to take you from understanding nothing to making you feel like you are ready to tackle the AP exam and just really crush it this year. So stay tuned for those review lessons. At the end of each lesson, Tony and I give you an AP practice exam problem to try, right? Those are unique questions, and I'm writing these questions to give you a glimpse of maybe how AP problems might look on the exam, right? How could we test you on something knowing that it's open book or open notes? How can the College Board test you on something knowing you might have a calculator or Google, and really still see whether you understand the ideas or not? And that's where those AP practice problems come from. At the end of each lesson, we give you one. And then at the beginning, our warm up is just to go through that. And so I would encourage you, if you haven't been doing it, take 5 or 10 minutes to try those AP exam practice problems, because that really is going to be good practice for the exam if you do those each day. So this is our problem from Friday that Tony left us off with. Consider the geometric series. He taught us about geometric series last Friday. The series K times the quantity K plus 3 over 6, all to the n power. And then part A wants us to find the sum of the series when K is 1. Part B, find the value of K such that the sum equals 12. And then finally on part C, that series converges between A and B, but it diverges at A and at B. Let's find those values of A and B. So let's see if we can solve these problems together really quickly. Part A says, let's find the sum of this when K is 1. So really, they told us that K is 1. So if I plug in 1 for K, I get a 1 here in front, and then plug in a 1 for K here. Well, 1 plus 3 is just 4, right? And 4 over 6 is going to be reduced to 2/3. And we know, hopefully we remember from Friday's lesson, that geometric series, as long as our ratio, the R value, is less than 1, or the absolute value of R is less than 1, then this geometric series converges. Well, in this case, our R value is 2/3, and 2/3 is certainly less than 1. So we know that it converges. And geometric series are really unique because it's the only series that we really have learned so far that not only can we figure out whether it converges or diverges, we can actually figure out what it converges to, right? We can actually figure out what the sum is. Whereas the other series, when we did alternating series test, or we did P series, right? And we do ratio test tomorrow, when we learn these other tests, we could figure out whether they converged or not, but yet we never knew what they converged to. And the geometric series is pretty powerful because it actually will give us a sum. And we learn that if a geometric series converges, we know that the sum is going to be A over 1 minus R, where A is the first term and R is that ratio. So in this case, our first term, if you plug in 0 for n, you get 1 times 2/3 to the 0 power. So our first term is just going to be 1 over 1 minus R. And we already have said our R was 2/3, so it's 1 over 1 minus 2/3. And if we reduce that, 1 minus 2/3 is 1/3, and that gives us 3. So when K is 1, the sum of the series is going to be 3. For part B, now it's the same idea, right? But the College Board is really good about writing questions, and they'll reverse things around at you a lot, right? Making you think about things inside out, working things frontwards, and then also working them backwards. And so here they're telling us the sum of the series equals 12. Let's figure out what K is. Well, we know again, a geometric series converges. It will converge to A over 1 minus R. Well, if this sum equals 12, then it has to converge, right? Otherwise, you wouldn't have a sum. And they're telling us the sum is 12. So in this case, instead of telling us what K is, they're telling us what S is. And we're going to hopefully work backwards. And so we know that the sum is 12. And then A is our first term. Well, how would we get A? We would plug in 0 for n, wouldn't we, to get our first term? Anything to the 0 power is going to be 1, and 1 times K in front is just going to be K. So our first term is K over 1 minus R. And what's R? Well, this is our R value right here for geometric series. And we get R is going to be K plus 3 over 6. And now we have an equation that we can solve, and we're just kind of back to basic algebra. There's a lot of different ways we might solve this equation. For me particularly, I like to multiply by 1, and I like to multiply by 1 by multiplying by 6 on top and 6 on bottom in this case. And so on the right-hand side, we multiply the top and bottom both by 6. And so I get 6k on the top and the bottom. If I multiply by 6, we're going to get 6 minus the quantity k plus 3. That got rid of that complex fraction that we had there originally. Notice I put the k plus 3 in parentheses because this has to be distributed. And so this gives me, I'm gonna use a little arrow here, 12 equals 6k over, this is if I distribute this minus sign here, it's gonna be 6 minus k minus 3, which becomes 3 minus k. And now I can multiply both sides by this 3 minus k to get rid of the fraction. If I multiply by 3 minus k, we're going to get 36 minus 12k equals 6k. And then a little bit of solving here, and we're hopefully going to agree that our k value is going to have to be 2, right? And then we have to be careful because we want to make sure that, in fact, this doesn't contradict anything, because remember, the only time we're allowed to use this series formula for geometric series is if the series converges, right? If our r value, if the absolute value of r is less than 1. So I got a k value. Let's double check now to make sure it wasn't some kind of extraneous solution. So if k is 2, then our r value in this case would have been 5 over 6. And that is less than 1, so we know that we're okay. So our k value is going to be 2. And then finally, in part C, we know that this whole thing converges when k is between a and b. But it diverges at A and B. Let's find out what A and B are. Well, remember, a geometric series converges when the absolute value of R is less than 1. Well, another way of writing that, to solve an absolute value problem like this, that's equivalent to saying that R is between -1 and 1. So if this is our R value here, we can say that -1 is less than k plus 3 over 6, which is less than 1. And now we're just solving this compound inequality. Multiply everything by 6, and we get -6 is less than k plus 3 is less than 6. Subtract 3 from everything, and we get -9 is less than k is less than 3. And there we go. There's our A and B values. We know that at 3 and -9, the series diverges. We can quickly check. If k is 3, this r value here becomes 1. And if r is 1, a geometric series diverges. And if k is -9, we get -1 inside of the parentheses for r. And if r is -1, a geometric series also diverges. And so in this case, A is going to be -9 and B is going to be 3. There we go. There's our solution to last week's AP practice problem, which is our warm-up today. So let's talk about what we're going to do today. Well, we're going to introduce the idea of radius of intervals of convergence with power series. We're also going to, probably more important for you right now, is we're going to connect and review the different series that we've talked about so far. We're going to put all these together. Most of the lesson today, we're going to be connecting to the geometric series that Tony talked about last Friday, but then at the end of the lesson, we're going to connect to all of those previous series. So what should you already know how to do? Well, hopefully you can solve an absolute value inequality. That's what we just did on the last part of that warm up. You remember a little bit about geometric series when they converge, the alternating series test for convergence, our P series and when they converge, as well as our nth term test for divergence. All those previous things that we've covered in previous videos are going to be brought together at some point during today's lesson. And by the end of the lesson, we'll be able to solve some of these really kind of cool problems, some problems that I don't think you could just solve on Google or a book, where if you're given a geometric series like this, what is the smallest possible sum for the geometric series? And so by the end of today's lesson, hopefully you'll be able to apply the things that we've learned to tackle a problem like that. So guided practice is kind of like the notes of the lesson, right, each day. So here's where we're going to start with. I'm going to tie this back really briefly to what we did on Friday, just to make sure we're on the same page, but we're going to extend this here to today's lesson here in about 30 or 45 seconds. And so consider the geometric series 4 times 1/3 to the n power. Does this series converge or diverge? Well, we know it's geometric, right? And so how do we know it's geometric, first of all? The dead giveaway for a geometric series is when the exponent is n, right? That's how you know something is geometric, is when the n in the problem, the variable of the series, is an exponent. That creates a geometric series. And our geometric series will converge if the absolute value of r is less than 1. Well, in this case, r is equal to 1/3, and the absolute value of 1/3 obviously is less than 1. So this series will clearly converge because it's a geometric series where r is between -1 and 1. Well, let's extend this to be a little bit more broad. Instead of calling it 1/3, we'll call it c/3, where c can be, just different various numbers. And let's figure out whether this converge or diverge for different values of c, right? And so what if c was 2? Well, if c was 2, that means that r would have been 2/3, right? And the absolute value of 2/3 is still less than 1, which means if c was 2, the series would still converge. But what if c was 3? Well, if c was 3, then r is going to be 3/3, and the absolute value of 3/3 equals 1. And a geometric series will only converge if the r value is strictly less than 1, right? If it's positive. So in this case, it equals 1. This would be a really good example of a divergent geometric series. And we can keep going through these different values, but it's kind of leading us to the idea of, instead of checking individual numbers, we're more interested in knowing what are all the possible values of C, right? We know that C would converge if C was 2, it would diverge if C was 3. We can kind of quickly mentally check that if C was -1, it would converge, but yet if C was -4, it would diverge, and if C was 0, I would claim that this converges. Okay, and so we have these different values and different kind of ideas to figure out how they converge or diverge. How would we list them all out? Well, first of all, there's an infinite amount of possibilities. We're not going to list them all out one, but could we list an interval? Is there a way to describe all the values of C that would make this series converge? And that brings up two interesting and important concepts in calculus. One of them being this idea of intervals of convergence, meaning what are all of the values of C that would make that series converge? And then secondly, this idea of a power series. The power series are pretty important ideas in calculus. We're going to introduce it a little bit today, but we're not going to go into a whole lot of depth because we're going to reinforce it more tomorrow with the ratio test, and we'll reinforce it more with our Taylor polynomials on Wednesday and Thursday as well. And so I just want to introduce it mainly to connect it to our understanding of geometric series. And so the definition of a power series is if x is a variable. So now what we're doing is we're creating another variable in the problem. So instead of having just an n in the problem, we're going to have an x and an n. And so a power series is a series where it's a sub n, x sub n. You can see the expansion here, where you have a sub 0, x, sub 1 of x, on and on and on, going on like that. That's called a power series. And it looks kind of like a polynomial, doesn't it? Think about what we talked about with polynomials. A polynomial, when you were in algebra, right, might look something like, 3x squared minus 4x plus 1. That's a polynomial, right? Well, here's the main difference. Number one, with polynomials, when we were in algebra, we started with the largest exponent first, right, to put it in a standard form, and we kind of went down from there. Well, a power series is going to start going up. And the reason why it's going up is because a polynomial has a finite number of terms, whereas a series has an infinite number of terms. They keep getting bigger and bigger and bigger and bigger. So we can kind of think about a power series as a polynomial that just keeps going and going and going and going and going. If a polynomial kept going and getting higher and higher powers of x, if we did that indefinitely, it turned into what we would call a power series, right? And you're thinking, well, how is that possible? How could you have an infinite a number of powers of x and have it be meaningful? How could that actually be anything? How could that equal anything? Well, that's what we've been doing, haven't we? we've been looking at all these series so far, and we've learned that we can have an infinite amount of terms, but yet the series can still converge. Even though we're adding an infinite amount of items, it won't go out of control or bounce back and forth sometimes. It will converge to a specific value. In the same sense, a power series for certain values of x, even though we're adding up an infinitely amount of them, could still converge to a very specific value. And then a more general case of a power series is going to be a power series centered at c. It's the exact same idea. Instead of just x, we're going to have x minus c in replace of all the x's. And we would say that this power series is centered at C. And so we're going to talk more about this a little bit more today. It looks a little bit overwhelming at first, but it actually ties in really well with what we've been doing already with geometric series. And so we're not going to spend too much time today on the background of power series. I'm just going to kind of throw it out there and we're going to do some stuff with it, and then we'll formalize it more later on. But we do want to connect it and make some parallels to our idea of geometric series from last week. So our geometric series from last week, AR to the n power, would just create this series. Now, if we let every R become X in this geometric series, if I just replace all those R's with X's here, we get this. And that looks a lot like what we had up here, doesn't it? It's basically a geometric example of a power series. Now, geometric series can be an example of a power series. There's other types of power series that we're going to learn about, but a geometric one is a really good example to help us kind of solidify our understanding or start to play around with power series a little bit today. And we knew for a geometric series that as long as the absolute value of R was less than 1, then the geometric series would converge. Well, if we're going to replace R with X, that means for our power series, for this example at least, we need the absolute value of X to be less than 1 to guarantee convergence. Now, tomorrow, Tony's going to get us into the ratio test, and we're going to learn there's some other types of power series that we can look at that aren't going to be strictly geometric. And so this reasoning that we have that absolute value of X has to be less than 1, this is going to be a condition for geometric power series in particular. So as the great Michael Scott would say, I don't come up with this stuff, I just forward it along, right? So I didn't create power series. I'm just going to be the person that's going to pass along these ideas to you today. So let's look at some examples here. So consider the series x over 4 to the n power. For what values of x will this series converge? Well, first of all, we see it's geometric, right? Because the n is the exponent. Whenever you see the n as the exponent, you know it's a geometric problem. So even though there's an X in the problem, I don't have to let the X confuse me at first. I always think it's easiest for me to look for the N first. And if N is only exponent in a series problem, it gets me into the mindset of it's a geometric type of question. And a geometric question tells me that it will converge as long as the R value, in this case, X over 4, as long as the absolute value of that is less than 1. And so writing our inequality, we know that -1 is lower than x over 4 is less than 1. Multiplying everything by 4 on this compound inequality, we're going to get -4 is less than x is less than 4. So what values of x will this converge? It'll converge as long as x is between, and not including, between -4 and 4. I'll let you try example 2 on your own after this video, but I want to get to some more interesting examples as well as some vocabulary that's going to become pretty important. So there's 3 really big words that are going to play a big role with power series. And even with Taylor polynomials later on, we're going to have the idea of a center, idea of a radius, and the idea of an interval of convergence. It's a lot of vocabulary words that can seem a little bit daunting at first, but here's what they mean. And then I think when we do some examples, it'll really solidify how to tie these ideas together. The center of a power series is the x value. It's the location, the x coordinate, where all of the terms, except maybe the first term, are going to be 0. Okay, and every single power series will converge at its center. Okay, so the power series, the center of it is going to be the x value that makes all the terms essentially just become 0. The radius of a power series is the distance, right? Think about radius of a circle. You start at the center of a circle, right? We have a center here as well. And on a circle, the radius from the center is how far you can go in each direction until you get to the boundary of the circle. Well, for a power series, it's very similar. We start at the center where we know the series converges, and then from there we can extend out in each direction a radius, a certain amount, and we know that that radius, the series will still converge as long as we're inside of that boundary. And if we go beyond that boundary, beyond the radius on the outside of it, then the series will diverge, right? And so the radius is how far we can go from the center and still have a convergent series. Sometimes the radius is 0, meaning it only converges at the center. Sometimes the radius is a finite number. You can go like 3 in each direction or 5 in each direction. And then sometimes the radius is infinite, meaning no matter how far you go away from the center, the series will still converge. And we'll see examples of all 3 of those, especially tomorrow in our unit on the ratio test. And then the interval of convergence is just the complete interval. It's the list of all those x values that will create a convergent series. On the last example, our answer, that was the interval of convergence. The interval of convergence is just basically the solutions. What are all the x values that would create a convergent series? And so in our initial discussion of our geometric series, we talked about if we replace r with x, we get this geometric power series, right? And we know that this converges whenever the absolute value of x, because x was our r value, was less than 1. And that means that -1 is less than x is less than 1. So if I think about this, it means this is going to converge anywhere between -1 and 1. Well, what's in the middle of -1 and 1? Well, 0 is right in the center of that. So 0 would be our center. And then from our center, we were able to move 1 unit to the right and 1 unit to the left. That is our radius of convergence. So this is our interval of convergence, -1 to 1. Our radius of convergence, which we use as a capital R, very different than the little r we use for geometric series. The radius is going to be 1, and then our center of the series is going to be 0. That's kind of a quick example of a basic problem, but let's take a look at an example where it's not going to be quite as straightforward as that, but you're going to learn pretty quickly that finding these 3 ideas is actually pretty easy, and they're really well connected. So once you understand what one of them is, it will help you find the other one. So let's find the center, radius, and interval of convergence of this geometric series. Notice the n is an exponent, so I know it's going to be geometric. And because it's geometric, I know that the absolute value of r, in this case, which is x plus 1 over 5, has to be less than 1, right? Because it's geometric. Now, I keep bringing up this idea that n is the exponent, so it's geometric, meaning I'm able to use this little shortcut here because the examples we're looking at are geometric. Not every example is going to be geometric, right? There's more series, there's more power series, especially besides ones that are simply geometric. And so these are nice examples to get us started with this because all the examples we're doing are geometric. Well, tomorrow with their ratio test, we're going to learn how to do a similar idea with series that are not geometric. So be careful of that. Don't just assume that we can always apply this technique. This is working because we're dealing with geometric examples. So for solving this, we already said that we know we can write this as a compound inequality, right? -1 is less than x plus 1 over 5 is less than 1. And then to solve this, I can multiply everything by 5, and we get -5 is less than x plus 1 is less than 5. And then subtracting 1 from all sides, we're going to get -6 is less than x is less than 4, right? And so if I think about this on a number line, here's -6, here's 4, and I know that my series converges between those values. So the interval of convergence, we're going to abbreviate that IOC right now. The interval of convergence is going to be -6 to 4. I'm using parentheses because we're not going to include the endpoints of a geometric series. It's possible if it wasn't geometric that the endpoints could be included. And then I have to also find the center and radius. Well, if I have a -6 and I have a 4, the center of those two values, what's right in the middle of -6 and 4? Well, mentally, we can kind of figure out that it's just -1, right? So the center is going to be -1. And then the radius is from that center, how far could we move in each direction, right? How far were we able to go in each direction from the center? Well, if we're starting at -1, we can see that we were able to move a distance of 5 in each direction, right? And so our interval of convergence was -6 to 4, the center was -1, and the radius was 5. Now, looking at our initial problem here, you can kind of realize that a lot of these numbers, like the center and the radius, they seem like they're connected somehow to the original ratio, right? Initial little r value for our geometric series, and they are. So let's talk about how that's connected. Kind of an easier way, I think, to find the center, radius, and interval of convergence is to think about this form right here. That when we're solving for these things, if we can get our problem to a form where we have the absolute value of x minus some value or plus some value is less than some other number, then this value that we're subtracting here, we're going to call it c, that's our center. And then the value that we have over here, once we get it in this form, is going to be our capital R, or our radius of convergence. And so we can find our center and radius really quickly, actually. And then from there, we can find our interval almost immediately. So let me show you a couple of examples of how using this form can help us avoid using those compound inequalities. And so let's find the center, radius, and interval of convergence of this geometric power series. It's geometric, again, because the only case of n in the problem is an exponent, which makes this a geometric type problem. And so since it's geometric, we know that the ratio, x minus 4 over 2, the absolute value of that needs to be less than 1. So what are we trying to do? We're trying to get this into this form. So instead of writing a compound inequality like we did in the last example, is there a way to make this look like this? And to make it look like this, really what we want inside the absolute values is just x plus or minus the number. We don't want to have any multiplication or division. And so to make it look like this, we can multiply both sides of the inequality by 2, right? And so we're going to get the absolute value of x minus 4 is less than 2. I multiply both sides by 2. And now look what we have. We have a form that looks like what we have here. Once we have it in this form, we can immediately conclude that the center is going to be 4. Remember, the center is the x value that will make all the terms become 0, right? And so if x is 4, then everything inside of here will become 0, and we get a whole bunch of zeros repeating, right? And so our center is going to be 4, and then the other side, once we get it in this form, is going to be our radius. Our radius is now 2. Big R is 2. So we've already found the center and the radius. How can we use that to find our interval of convergence? Well, all we have to do, I like to make a little number line. It helps me think about this pretty easily. The center is 4. That's the center of our power series. And then the radius is 2. Remember, the radius means how far you could go from the center in each direction. I can move 2 to the right and 2 to the left, which means this is going to go to 2. If I subtract 2, it's going to give me just a 2. There shouldn't be a negative there, sorry. And then on the other side, if I add 2 to this, it's going to give me 6. And so my interval of convergence, my complete interval, is going to be the open interval from 2 to 6. So let's try another example here. We can kind of take it even one step further. For what values of x will this series converge? And then on top of that, what is the sum of the series for all those values of x? Well, first of all, when it says, for what values of x will the series converge, that's just another way of asking for the interval of convergence. So how do we find the interval of convergence? Well, the same way we just did. We would take the absolute value of x plus 2 over 3, and we know that has to be less than 1 because it's geometric. And we want to get it into this form where we're not dividing or multiplying by anything. And so we would take this and then multiply both sides of the inequality by 3. And now by looking at this, we know the center is going to be -2, right? Because it's -2 plus 2 would give me 0. And then our radius, or capital R, is going to be 3. So using our number line again, our center is going to be -2, and we're going to move 3 in each direction, which means if I go backwards 3, I'm at -5. If I go forwards 3 from -2, our center, we're going to get 1. And so the x values are going to be any x value between -5 and 1. So that answers the first part. What values of x? Well, the values of x were x's between -5 and 1. And then what is the sum of the series for those values? Well, remember, the sum of a geometric series is just going to be a over 1 minus r, where a is the first term and r is the ratio. Well, a, the first term, is what we would get by plugging in this lower bound for n. So if n is 0, we get x plus 2 over 3 to the 0 power. Well, anything to the 0 power is 1. And then 1 times 4 in front is going to give me 4 for my first term. And then over 1 minus r. And r in this case is going to be just x plus 2 over 3. This is our sum, and we can leave it like this. We don't have to simplify it. Basically, for any x value between -5 and 1 that I plug in here, I know the sum would equal whatever this is if I plugged in the same value of x, right? This formula would only work for x values that are between -5 and 1. All right, so a couple of things, putting it all together for us today. Going back to what we've learned before, right? The nth term test says if the individual terms of a series do not approach 0, then we know the series diverges. If the terms do approach 0, then we don't know, right? It's inconclusive. We have to use another test. The p-series test from last week is when n is the base, and we know that if n is a base, a p-series will converge whenever p is greater than 1. Geometric series, what we talked about Friday and again today, is AR to the n power, and that will converge when the absolute value of little r is less than 1. And not only does it converge, it's the only series so far that we're going to talk about that we actually know what the sum of the series is. And then our alternating series test from last week says if a series is alternating, it will converge if two conditions are met. Number one, the limit of the terms approaches 0. It has to pass the nth term test, basically. But also the terms have to be decreasing at some point on. And so this is another Michael Scott quote. There's a lot of office quotes, I think, that really are apropos for what we're doing in Calc BC. He says, and I knew exactly what to do, but in a much more real sense, I had no idea what to do. Is that ever you, where you feel like you understand the topics in Calc BC, you understand series and convergence, or you think you do, and then when it's all mixed together, you're like, I know what to do. But when it's all mixed together, I feel like I have no idea what to do. And so one little tip that I'll give you, my dog Buddy here, he's got his smart glasses on, and he'll give you a little bit of tip here. And he'll always say, this is my dog here, he'll say, find in. I think a really good way to start these problems when you're overwhelmed is to find in the problem. Kind of like Find Waldo. Remember those Where's Waldo books? I was going to have a nice picture of Where's Waldo, but I'm pretty sure that's trademarked. If I put it up here on the screen, we could be booted off of YouTube forever. And so I don't want to do that and risk getting in trouble. But find in the problem. And so for what we're doing, especially this year, there's a couple of examples. If n is the base of the problem, right? It's a base. Then we know it's a p-series problem. If n is the exponent of the problem, then we know it's going to be geometric from Friday. And then a third case would be, what if n is a combo of those two, meaning it's a base and it's an exponent? Or what if it's just something different, meaning like what if you had n factorial, or what if you had n squared and then 3 to the n, where it's both a base and an exponent? It's a combination of things or something different. That's what we're going to look at tomorrow, and that's going to be a really good example of when we would use the ratio test. But I think a really good first step when you're putting all these together is to find n in the problem. If n is a base and only a base, think p-series. If n is an exponent and only an exponent, think geometric series. And if n is a combination of things that has different roles at the base, but it's also an exponent, or it's got a factorial, something kind of weird going on with n, think about the ratio test. And so if you think about where n is first, I think it's going to help you have a better idea of what to do on these problems. And so I know we're short on time here, but I want to give you a chance to put this into a little bit of practice here. And so we're going to find the center, radius, and interval of convergence for this series. And so I want you to try this. I know I have the timer here, and the timer says 2 minutes. I'm going to put it down to 1 minute, but I'm not even going to give you a full minute because we only need a few seconds. So see if you can try this right now. See if you can do it on your own. That's really an important step, is to see if you can do this. And I'm going to put the timer on here, but you're only going to get about 30 seconds. And I'm going to play some nice music that Kareem shared with us. Awesome. Thank you, Kareem, for that. So let's go ahead and see how you did on this problem. Find the center, radius, and interval of convergence. Well, from what we just talked about, we knew that this is geometric, right? And so it's going to be the r value, little r, is the absolute value of x minus 4 over 6. That needs to be less than 1 for a geometric series to converge. And if we multiply both sides by that 6, right, we get the absolute value of x minus 4 is less than 6. And since we're in this form that we are kind of wanting, we know that the center is going to be 4 from here. And big R, the radius of convergence, is going to be 6 right here. So we got the first two figured out. And then the interval of convergence, we just start at the center of 4, and we know we can go 6 in each direction. So 4 plus 6 will be 10. And then 4 minus 6 is going to be -2. So our interval of convergence is going to be -2 to 10. Let's refresh what that means, right? What do I mean by interval of convergence? That means you can plug in any x value you want between -2 and 10, and any number you pick between there, this geometric series would converge. And anything that you pick beyond those numbers, including -2 or 10, this geometric series would diverge, right? So we're finding all of the values where this series would converge. In the handouts and the Dropbox, you're going to see some additional problems, right? And I kind of skipped to practice 3 here, just to give you an example of what it looks like. The series 2 times x plus 3 over 4 to the n power has interval of convergence a to b. Find the limit as x approaches a from the right-hand side of the series. And as Kelly Kapoor would say from The Office, I have a lot of questions. Number one, how dare you? This is how my students, I think, look at me when I ask questions like this, right? We give them kind of a simple example. Oh, I get this. This isn't so bad. And I throw a problem like this on there, and they're like, how dare you ask me that problem? Well, here's what I want to tell you about problems like this. These problems have a much worse bark than they do a bite, meaning they look a little bit scary on the surface, but if we understand the idea behind series, these problems actually aren't that bad, right? Notice I tell you it has an interval of convergence. Well, could we find the interval of convergence? Sure, we could. And then once we find the interval of convergence, we now know what A is, right? And then the second part is find the limit as x approaches a from the right-hand side. Well, of course, x has to approach a because we can't converge at a. Remember, on a geometric series, the endpoints will not converge, but we can get closer and closer and closer to a. So as x gets closer to a, let's find the sum of this. So once we know what a is, we can write an equation for the sum. We did that on one of our examples, find the sum of this, and then all we're going to do is find the limit of that as x approaches that value of A. So I'm going to leave that one for you, but you're going to have some nice worked out solutions. So this is a good example again of how can the College Board write questions? How can we test you on this exam when we know you're going to have notes or Google or other things available to you? Well, questions like this would be a really good example of you're not just going to Google a problem like this. It's a little bit more abstract, a little bit more conceptual to get to the heart of whether or not you understand his ideas. And you can't just Google something or look up an example in your book, right? Um, and so a couple of other ones that we're not going to look at, but I want to point them out to you is going to be now we're connecting some of our ideas together, right? For which integer values, that's a key, do both of these series converge? Well, what do you notice about this problem? I'm thinking the first one here, notice the n, right? Remember I said the first step on a series is find n. Well, the first series, n, is here, and n is an exponent, right? And if n is an exponent, that means the problem is geometric, right? And if it's geometric, now we know that the R value, which is this, needs to be less than 1. And we could solve this and find the interval of convergence. Well, on the second example, again, let's find n. Well, n is here. N is not the exponent now, is it? N is now the base of the problem. It's not an exponent at all. N is the base. And if n is the base of a series, then that means it's going to be a p series, right? And for a p series will converge if the exponent, in this case 2x minus 11, is greater than 1. And we could solve that inequality. And when we solve both of these inequalities, we're now going to try to find an overlap, right? And so this is a good connection between things we've done before, as well as things that we're looking at now. Um, as a special treat for you, I create these activities called Big Tens, and Big Tens are things you may have done. If you're a student, you may have done them in your class. Your teacher may have shared some with you. If you're a teacher, you may have seen them on the Facebook group, or if you've been in my workshops, you certainly have seen them. I create these Big Ten activities where you're going to see a box at the top of the page, and you're going to see the numbers 0 through 9, and there's going to be 10 questions, right, that go along with the activity, and each question should have an answer 0 to 9, and it should be a whole number 0 to 9. So it kind of gives you a built-in check to make sure you're on the right track without just giving you the answers. And so if you get an answer, for example, of like 11, well, you know you made a mistake. That's not a number between 0 and 9. Or if you get like a decimal, like 1.5, or 3/4, you know you made a mistake because that's not a number between 0 and 9. Every answer should be a number 0 to 9. And if you do it correctly, you will get all 10 numbers crossed off. Now you have to be careful on these because I purposely think about what are the big mistakes, what are the big misunderstandings and misconceptions that students make on the exam. So I purposely will write questions to check for that. And so if you get 5 for an answer, you cross off 5, you're feeling pretty good about yourself. Then all of a sudden, 4 problems later, you get 5 again, and you've got 5 twice. That can't happen. You know you made at least one mistake, right? Because if you do it correctly, you'll use every number exactly once with the 10 questions, and you'll cross them all off. So you're going to see a large variety of problems. Some of them are a little bit more easy, some of them a little more challenging, more conceptual, but they're going to give you some good examples of whether or not you're ready for this year's AP exam. And so this is just a little snip of the activity. There's question A, D, I, and J here to kind of share with you some of the different levels of questions, right? And so this is a brand new one, by the way. And so this has never been seen before. I'm giving it just to you right now. I feel like one of those telemarketing guys on those commercials, right? If you order right now, you can get this for free. But this is free for you. It's in the Dropbox. The whole activity is for students and teachers alike. But a couple of snippets of the types of questions that you might see. How many of these series are conditionally convergent? So what I've done is I've combined all of the series that we've talked about so far, all the lessons in Unit 10 that Tony and I have addressed or taught are going to be in this Big 10 activity. Just the things we've learned so far. Nothing else beyond this or before this, just what we've talked about in these YouTube live lessons. So how many of these are conditionally convergent? Which of the following series diverges by the nth term test? For which value of p would both of these series converge? Find the value of k. So the sum of this equals 2. So if you've been listening to these lessons and doing the problems with us, you've seen problems like this in each of our lessons. And now we're going to have a chance to put it all together. So here's a snip of what that activity looks like, but the whole activity is in the Dropbox. And we'll make sure we have a key in there for you as well by this evening. So let's do a little bit of debrief and summary as we wind up here. Today, we talk about a couple of things using limits to help us determine a finite sum for infinitely many terms using geometric series. And then we talk about power series a little bit, right? And so we didn't go super in depth behind the theory behind power series, and we're going to keep building on that in the next coming lessons. But we're going to hopefully give you better and better understanding of power series as we talk about ratio tests and Taylor polynomials and Taylor series later on this week. Be really careful. We have two different R values now, right? With geometric series, we have this little r, which is going to be the ratio, and then we have this big R now that we're talking about power series, which is the radius of convergence. They're not the same thing. Be careful about using lowercase and uppercase and what those two things mean. So your AP exam practice, which Tony will do tomorrow as his warm up, it's a good one. If you have a chance, you can watch this and take a photo of it. But again, it's in the materials in the Dropbox. If you have this printed off, you can find it. But it'll give you a good way to tie what we did today, as well as what we've done in previous lessons. And then this part C is really a good question, I think, because it's going to tie into what Tony's doing tomorrow. We'll see how many of you can extend your understanding of what we've done so far to part C. So give us a chance. It should only take you about 5 or 10 minutes to kind of think about this. It's not very algebra heavy. It's more of conceptual understanding. So try that and see how you do tomorrow when Tony will walk us through this and see how we did. A quick reminder, the College Board is very aware that not everybody has access to technology or ways to get to these AP Live videos or even the AP classroom problems, or maybe you're concerned about even taking the AP exams online this year. So they want to make sure that everyone has the resources they need. So if you or somebody you know might have an issue with technology, please, please, please share this website, cb.org/tech, and make sure that everybody has the resources that they need. So I hope at the end of this, as Kelly Kapoor would say, is, guys, I'm like really, really smart now. Like you don't even know, right? After these lessons, you guys are really, really smart now. People need to understand how great you are. So thank you so much for tuning in today with us. I hope you'll stay with us tomorrow as Tony goes into the last convergence test, the ratio test. And I will be back here on Wednesday as we try to clone my dog Buddy, because the world needs more buddies in this world. Have a great day, and we'll see you tomorrow.